There's a really nice substitution that I like, and it's called the Weierstrass substitution. How does the substitution works? To investigate this, I like for us to focus on this integral. So what's wrong with this integral? Well, if you're like me, who says the substitution is trigonometric substitution, you will find this really difficult because the cos square x is really disconnected in this integral, and there is a usual way of solving this, which is this method. So what really bothered me about this method was the fact that t was need to be tan x. That was the substitution we're supposed to know from the get-go, and it really bothered me because it feels like you pulled it out from the air. There was no really instinct there of why this and this. Thus t is equal to tan x and the whole integral collapses. So how do you fix this? Well, to fix this, let's just forget the fact that I just showed you that method. Now we'll have to use a different approach. You see, cos can be inverted to sec, and the reason why I want to do that is the fact that sec has this nice relationship between tan. This is the fact that if you differentiate tan, you get secant squared, and secant squared has a really nice relationship again with tan due to its trigonometric identities. So we can capitalize on that if we then implement this on this integral. Check it out. The whole integral condenses to what we can integrate with trigonometric substitution. And now we've landed on the same answer as before. So this is why t was made to be tan x, because that's the only substitution. We could skip all the whole part of multiplying the secant square on the denominator and the numerator. We just had to say t equals to tan x, and the whole thing will collapse. But it doesn't end there. It doesn't. This time we are going to take a slightly variation of this integral, one that comes without square. And now I'm just going to show you how we solve it with the usual method, and then I will implement another approach. So similar to before, the main question is why tan x over 2? To answer this, we must try to see the difference between this integral and the previous integral, and that's that the cos isn't squared. So the question is, could we massage this to give us cos squared? And yes, we can, using double angle identities. Now it looks familiar as the integral that we treated before, and I trust you know what to do from here. So here are the forms to which we can apply the first and second approach respectively. To illustrate this, I'll be taking on another integral, one that deals with some combination of sine and cosine using my approach. And you see that it correlates with that of the Weierstrass substitution methodology. But here's an integral that could actually give an answer that looks different in appearance as that of the Weierstrass substitution methodology. And the reason for that is that trigs are connected in some loose sense, having a constant by their side. This constant is always absorbed by the average constant C.